Now what we want to do is relate these three. Okay, we want to relate these three quantities. We want to say, let's say, the acceleration that results from a force. We have an object of inertial mass m, this amount there, this amount this. We push on it with a certain amount of force, and it gives rise to a certain amount of change of velocity. Let's say the velocity was 4 meters per second, and now it's 5 meters per second. So the change, we'll learn how to define that later. We change a certain amount. We have a certain amount of acceleration, change velocity. What should that depend on? Well, obviously, it's going to depend on these two factors. There's no other factors that it could depend on. Right? We eliminated all the other factors. How will it depend on this? How would we write an equation? And then I don't want to hear the answer from somebody who learned it before, but in other words, we're trying to discover. How would we, A is going to depend on F and N. There's only two things it could depend on. How will it depend on it? What do you expect to see? What kind of relationship should it, it's not even math, what kind of relationship should there be between them? What would your intuition say? How would you start from scratch? You've never seen anything, you've never heard of this. You know that a force on an object of mass m gives rise to acceleration. You want to know the acceleration equals, what should we put here? Okay, acceleration equals force? Is that right? I mean, well, again, not based on anything you heard before, but why should we put force? What does this mean, acceleration equals force? What would this mean? Let's say if this was our equation. Why would we say this equation as it stands? Not that you're saying that this is the right one, but let's say if I wrote this equation, would you be able to tell me, no, that can't be right?
Let's say force is the same as acceleration.
Right. No. You're saying that it's not right because here I'm saying that force is acceleration. Well, force is not acceleration.
Right.
But there's two things that this, you're right. One of the things it says maybe is force is acceleration. But this equal sign means something a little bit different. What does it mean? It means equal to. It doesn't mean necessarily is the same as. Okay? In other words, I can say 3 plus 2 equals 4 plus 1. What do I mean by that? I mean the sum of these two is 5 and the sum of these two is 5. I don't mean that 3 plus 2 is 4. It's not. 3 plus 2 is 3 plus 2. It's not 4 plus 1. Okay, but the sum of it might be the same. But you're right that this probably is not correct because it seems to say that acceleration is force. But it might be correct if we're saying acceleration equals force. In other words, what would that mean, acceleration equals force?
The result.
Right. That's the main reason why this equation is not true. Because we didn't put in F. We said it depends on mass, and according to this, the elephant and the ping pong ball move the same way. Which could be. There might be some universe in which there's no such thing as mass. Okay? But what would it mean then that acceleration equals force? Force is force and acceleration is acceleration. How could they, like you said, how could it be that they equal each other? Let's say there was a universe like that. Is it possible? The answer is it depends on what we call the units. That's the problem here. What is, like if I said, this length equals its mass, right? Could it be that its length equals its mass? Why yes and why not? Okay, let's say if it's 3 feet and 3 pounds, then you say the number of pounds is equal to the number of the weight. How about if I use kilograms? And 3 feet is not equal to whatever, 1.1 kilograms, no? So, and let's say I use yards. It's 1 yard, 3 pounds. Or what, right? The units matter. So when I say this equals that, I have to specify what units am I talking about. Okay? But otherwise it doesn't tell us anything at all. So force is equal to acceleration, depends on what units. But let's say I define the units in a certain way, and I say the amount of acceleration in a certain kind of units equals the amount of force in another kind of units. You know, that could have been. It might be that if you exert 2 units of force, you get 2 units of acceleration. But then you have to define them in an appropriate way. But we know that it's not true because it doesn't. Okay, so this is not correct. So we need to have some function or something which depends on m and f. In mathematics, we don't need to do this, but we would write acceleration is, we write it like this. Acceleration is a function of the mass acceleration, what kind of function should it be? Make up something that doesn't make sense, but it includes both mass and force. Just make up. What? NF. Okay. A equals NF. Good. All right. A equals NF. That's an equation. It incorporates all three. It's a possibility, right? It's a candidate. Can we rule it out? What might not make sense here?
Times.
Okay, m times f. Let's say NF being m times f. Okay. Why would you say that this doesn't make sense? Think about it.
What's the initial
The
force?
acceleration will increase if the mass is bigger.
Okay, so in other words, what we're saying here is take a certain amount of force and a certain amount of mass, you get a certain amount of acceleration. Double the amount of mass, add 2 elephants instead of 1 elephant. What do you get according to this equation? Does the acceleration get bigger or smaller? It's bigger. Triple the mass, you get 3 times as much acceleration. Does that make sense? Make 3 elephants should move with 3 times the acceleration as 1 elephant? It doesn't make sense. Okay, this equation can't be right.
Okay.
Okay, let's try another one. M plus F. Could that be right? Why not? As the mass, okay, so let's say F minus M. Could that be right? Okay, so the mass gets bigger, the acceleration gets smaller. You have F minus M.
No, it has to be equals something divided by n.
Why not this? But this gets smaller. The acceleration gets smaller when the mass gets smaller. Get bigger, right? If the force is, let's say, 100 and the mass is 20, so the acceleration will be 80.
But
The
you're
mass
gonna
is
get
40.
negative.
Okay, you can might get negative numbers here, right?
Okay.
If the mass is bigger than the F. How about if the force is equal to the mass? Let's say you have a force of 20 and a mass of 20. So the acceleration will be 0. Does that make sense? That's why it's not going to move at all. There's a certain, you have a mass and you have a certain force, you push on it and nothing happens. I mean, again, there could be a universe in which that's true, but it not as we know. Okay. So this equation doesn't make sense for those 2 reasons. And you can't just rule it out for nothing. There's a good reason to rule it out. Okay? What other kind of equation is there? It could be something complicated like m cubed times the logarithm of 3f squared.
Yeah.
You know, it could be. Why not? Right? Can you rule that out? Okay, you can rule it out again because of this n. But maybe we can find some other way. What way can I put in this equation here that you wouldn't be able to rule out? Give me some complicated, crazy equation that makes sense. Yeah, okay, let's start with the simplest then. Okay, give me another equation. What's another equation over here that you could propose that maybe makes more sense? Now that we've tuned our intuition a little bit, what might work? Pardon me? Why? No, we're doing acceleration equals. Okay. How would you? What kind of formula would you do? Okay. What we found was we ruled this out because we know that the acceleration should get smaller when you increase the mass. What's a mathematical way of guaranteeing that something gets smaller when something else gets bigger?
Division.
Division. All right. So if we had A equals something over M, as M gets bigger, what happens to A? It gets smaller. So that at least has that property correct. Now, what about force? When you make the force larger, what should happen with the acceleration? Larger or smaller? So where would you put it in this equation? Top. So in other words, this is a better candidate, right? Because it incorporates all 3, and it has M in the right proportion, the right ratio, and F in the right ratio. All right? But it's like almost too simple. I mean, maybe it's logarithm of F squared and sine of 3m to the 4th. Okay? Do you know that it's not that? You don't know that. You have to test it, right? As it turns out, it's this. That's amazing. It's the simplest possible formula that could possibly result. A is equal to F over M. It can't possibly be simpler. Newton's second law of motion, the acceleration of an object is directly proportional to the net force acting on it and is inversely proportional to its mass. Again, exactly what we said. The direction of the acceleration is the direction of the net force acting on the object. What is F equal to, just from algebra? A is equal to F over M. What's F equal to? M times A. So this law is usually written F equal to MA. Doesn't really matter which way you write it, mathematics. How would you read this? This one would be read as the acceleration of an object upon which a force is exerted is equal to the amount of force exerted on it divided by the amount of mass it has. Doesn't have to be exactly those words, but that's what A equal F over M means. Exert a force of F amount on an object of mass M, the resulting acceleration will be A. Two different equivalent ways of reading this equation. The same thing over here. F is equal to MA. What does that mean? How would you read, let's say somebody volunteer, maybe something you should volunteer, or how would you read? It's not F equals MA, obviously, but how would you read that? The way I said it here is the acceleration of an object of mass M when it experiences a force F is given by this equation. Or a better way, if you exert a force F on an object of mass M, the resulting acceleration is. How would you read this? I don't know. Somebody else? Anybody want to volunteer? How would you read this equation? Or you know what? Let's try read this equation. Somebody volunteered to read this equation. Either the way I read it or some other way. But not just A is equal to F over M. Anybody? Okay. All right. Somebody else? Maybe? That's right. Okay, this is very important. Okay? I want to do it again until you feel confident. I have it written out in some of the notes that I'll give you. Okay? You should be able to read this equation, not just A equals F over M, but the reason you should be able to read it that way is because when you're solving problems, it suddenly won't be clear anymore which A you mean, or which F you mean, or which M you mean. That the acceleration of an object that is experienced by an object, or that you see in an object, as a result of the force F being applied on it, when it has a mass M, is given by this equation. All right? To say it in an English sentence altogether, you would say something like, the acceleration of an object is equal to the amount of force on it that's causing the acceleration divided by the amount of mass it has. Okay, so that was just one sentence and incorporated the whole equation. All right, so practice saying that equation in a grammatically correct single sentence in English. All right, it's very important to understand the equation and very important in applying the equation to problems. All right, it's not trivial. It's not so simple as you see by the fact that you don't want to raise your hand if you're not sure what to do. Do the same thing with this, F equal MA. Make sure that you can say this equation as a grammatically correct English sentence. Like, the force on an object, F, is given by the product of the mass of the object undergoing acceleration and the acceleration itself. Something like that. Make a sentence in English that's grammatically correct, that incorporates a whole. And look at the logic of this equation in the same way that the logic of this equation is clear. Look at the logic of this equation. Does it make sense? And what does it mean? If I change the M, should the F get bigger or smaller? If I change the A, if I change the F. Look at these two forms of the equation. Or you can look at the third form of the equation. What's the third form of the equation? M equals F over A. Look at this one too. See if it makes sense to you what this means. Okay? When you can see those three forms of the equation and make an English sentence that's grammatically correct, describing them, you're beginning to understand it and you'll be able to apply. You can't even imagine a universe in which you would come up with a simpler equation than A is equal to F over M. It has just three things. You exert a force on something, the thing accelerates. What determines how it accelerates? Something, it's not just you exert a force of 20, it goes to 20, you exert a force of 50, it goes to 50. Depends on the object. right? You want something to be there that depends on the object itself. There's only one thing that's determined by the object itself. There's only one thing that's determined by the thing that's causing the pushing force. And this is the result. It can't be simpler than these three. It's hard for us to imagine a universe where we have something less complicated than these three. It's hard to imagine a universe which is so simple. It's incredible that it's so simple. It's so logical. And this equation is a general equation. It's not for the motion of a sailboat, the motion of the wind, or the motion of any object in the universe which moves with a changing motion, in other words, with a changing velocity, in other words, with an acceleration, moves according to this formula. It's really extraordinary. Okay. What we're going to be doing later on is solving this equation in different kind of systems, different kind of examples, and so on. But what you see here is some of what physicists would call the beauty of nature, or the beauty of physics. It's just so elegant and simple. Now, sometimes, of course, somebody's standing and say, well, it's not so simple, it took an hour and a half to do, and you have to have some algebra, you have to have relation. You have to know a lot in order for it to be simple. It's not simple in the sense that you don't need to know anything. And the same thing with more advanced physics. You have to learn a lot. But when you learn all that, you see how beautiful and simple it is. Okay? So hopefully we're going to be covering a number of equations which will develop in a similar way to show how simple it is. Okay. The force gives rise to an acceleration. F is equal to ma. The force is like the cause, and the acceleration is the result. Okay? Obviously, mass is not a vector. It's a scalar. It doesn't have a direction. So if F is equal to ma, and F is a vector, and a is a vector, then the direction of a is the direction of F. Okay? So we know that if it's moving with an acceleration, then the direction of the acceleration is given by the direction of not exactly F, but the sum of the forces. Right? All the forces added together, we learn how to take bunches of vectors and add them together. We don't care about the 100 vectors, we just care about the resultant. We look at the resultant vector, and then that's the one that we're interested in, the resultant force. Okay? And that will be equal to ma. In other words, the resulting acceleration will be given by this equation, or a equals sum of the forces over m. Actually, if you do the sum of the forces, you don't need resultant. The resultant is the sum of the forces. Okay? So a will be the sum of the forces over m. This sum of the forces is one vector. You're adding many vectors together, and the sum of the forces is one vector. So I'm going to write it like this. Sum of the forces is one particular vector, and take that magnitude of the vector and divide it by the amount m, you get a vector pointing in the same direction, just a little bit smaller. The magnitude is divided by m. And a will be exactly that. It'll be in that direction, the direction of f, with the magnitude reduced according to the amount of the mass. Okay? Sum of the forces acting on the object m, of mass m, is equal to m times a, we put a little m over here. This is the acceleration of the mass m due to the resultant forces acting on the mass m divided by the amount of the mass m. Okay? Maybe you take a boat or a plane, you know pretty well that when the train or plane or whatever it is moving smoothly, you can't tell it's moving until you look outside. It may be that if it's a train that's rocking side to side, but that has nothing to do with forward motion, right? You don't really feel the forward motion. If it changes direction, or if it slows down or speeds up, then you feel it. But if it's moving constantly, you fall asleep, you wake up, you have no idea if you're moving or not. If you've been on a plane, you know you can move at hundreds of miles an hour and have absolutely no sensation of motion whatsoever. Okay? In your frame of reference, the laws of physics will be the same. In other words, if you play a ping pong game on a train, the ball won't move differently than it usually moves. If the windows are open and there's wind rushing in, of course, it'll affect it. That would happen if it was stationary and there was wind coming in. Okay, the wind may be caused by your motion, but that doesn't matter. It's not the motion that's causing the change, it's the wind. If there was no air, or if the windows were closed, it would wind. So it's not the motion. If you're in a plane, you're moving hundreds of miles an hour, or if you're in a fighter aircraft and it's thousands of miles an hour, it doesn't matter. You're not going to do any physics that's going to let you know that you're moving. no way that you can determine that you're moving unless you look outside. And if other things are moving with you, then you won't be able to tell. And you probably all have the experience where maybe you're on a train and you think that you're moving, and what happens is a train that started backwards. How many people have had that experience? In a car, in a train, somewhere? A few of you have, okay? It's a kind of vertigo. You're sitting down and then you think you're moving, and what happens is there's another train going by the other side, and your eye knows already, your brain knows already that you're not going to feel motion, you're only going to see it. So you see something moving next to you, and your brain tells you you're moving ahead, and then suddenly you realize you're not moving. It's kind of like a switch. Yeah, it's an interesting sensation. Now, it's not obvious that it has to be that the laws of physics are such that they wouldn't be affected by motion. Okay, I mean, the universe could have been different, and maybe you would have been affected by motion. All right, but as it turns out, the laws of nature are such that if you're moving uniformly, basically, you won't feel motion. All right? Anything that you do, any laws of physics that we discuss, will be true whether you're moving or you're standing still, as long as you're moving uniformly. You're not changing direction, you're not changing your speed, okay? Or as we learned with velocity, you're not changing your velocity, right? Which means you're not changing either your speed or your direction or both. Now, in general relativity, you have a more advanced formulation of that law, okay? But for our needs, basically, if you're moving in uniform motion, there's absolutely no way to determine it. How you're moving is called the frame of reference. And in physics, we always describe things relative to your frame of reference. So if you say, well, I'm standing still, I don't feel any motion, I'm not moving, you say, well, okay, that's very nice, but where are you? You say, well, I'm on the train, such and such. You say, well, that train is moving from New York to Washington. You say, well, I don't feel any motion. In my frame of reference, nothing is moving. And let's say you see, I see there's something moving. Somebody just threw a ball backwards. Let's say one person standing on the platform, all right? Another person's on the train, and there's like a long window, all right? And somebody just threw a ball very quickly in the train backwards against the direction of the train. Let's say the train is moving at 30 miles an hour, and he threw the ball at 30 miles an hour backwards. From the frame of reference of the train, there's a ball moving like this at 30 miles an hour. What is the person on the platform going to see? Standing still. I mean, if the train is moving 30 miles an hour, right, and the ball is moving 30 miles an hour in the train, then the total speed of the ball relative to the person standing outside the train is zero. Because the train is carrying it at 30 miles an hour, but the person threw it at 30 miles an hour. So until the ball falls, at least, what's going to happen? What are you going to see? The train is moving this way, the ball is moving this way, and the train at exactly the same speed. So basically, it's going to be hanging in the air relative to this person. Okay, do you see that intuitively? Okay. If you did throw the ball, if you're holding the ball in your hand, you're going to see the ball of the person moving off at 30 miles an hour. When the person throws the ball, right, the ball's just going to be, you're going to see the train going by, and the person who threw the ball going by, and you're going to see the ball here. And as it falls, it's going to fall straight down. Okay, can you see that? Because it's moving at 30 miles an hour, and the train's moving 30 miles an hour, so it's going ahead. So from your frame of reference, standing on the platform, as far as you're concerned, there's a ball falling straight down due to gravity. Okay? Now, there's a principle, Galilean invariance and so on, that the laws of nature, as I said, don't depend on the speed at which you're moving with its uniform speed. Now, we can deduce from that something interesting that we spoke about in the previous class. There's an ice skating rink on the train, and there's an elephant on ice skates going that way. Okay? What happens? If he's moving with the speed of the train, he's not moving at all. Now, what happens if he slows down, right? The elephant is moving at 30 miles an hour down the ice track in the train. You're looking through, the train is going by, right? The elephant handler is going by, the elephant is standing still as far as you're concerned, with the ice underneath him flashing by. The elephant is standing still. Now, what's going to happen if there is some friction? The elephant is going to move from 30 miles an hour to, let's say, 29 miles an hour, right? As the train is going by, depending on how long the train is, okay? What's going to happen as far as you're concerned? Okay, can you all picture that? You have the elephant is moving at 30 miles an hour, and the train is moving at 30 miles an hour. Now, what happens if he slows down? Right? The more he slows down, the more the train is going to start carrying him along. You see that? If he was standing still, he'd be carried along at 30 miles an hour. The other extreme is if he's going at 60 miles an hour, he's going zipping by you even if you're standing here. If he's going at 30 miles an hour, he's standing still. If he's going at 29 miles an hour, he's moving at how fast this way? 1 mile an hour. The train is pulling him 30 miles an hour this way. Every hour he's moving 29 miles this way. So every hour he's making 1 mile that way. Okay? So he's going by you at 1 mile an hour. Now, let's say you're standing on the platform and you see this elephant on ice skates and he's not moving. Okay, you don't even see, let's say, the ice skates. You just see an elephant in the big window. You don't even see the train. You're just looking through and you see this elephant right in front of you, standing still. Okay? Now suddenly you see him start to move backwards. What would you say happened? If something is standing still and then it starts moving, what must have happened?
The train moved faster.
Okay, let's say, not the train specifically, but let's say in terms of what we discussed in the first class, I think it was, something is standing still and it starts moving. What can you tell me? What must have happened? Something changed, obviously. What? Force. Something exerted a force on this to make it start moving. It wasn't moving. Something made it move. Right? Now, from the perspective of the train, what happened? Why did it change its motion? Because, let's say, the friction on the ice. What I'm trying to show you is that intuitively, if we assume that the laws of nature are the same, even in a moving frame of reference, then for something to slow down without a force acting on it is just as impossible as for something to start moving without a force acting on it. Okay, we might think that to start moving, you certainly need a force. That's our intuition. To stop moving, we might say, well, everything stops moving eventually, right? That's the way the ancient Greeks thought and everybody else thought. To stop moving, well, that's the natural state of events. Things stop moving by themselves. To start moving, it was clear that you needed something to push. What this can show you is that they're both equally impossible if we accept that the laws of nature are the same in moving reference frames. To start moving and to stop moving both require a force. How do we see it? Because if this elephant is in the train, right, on the train we would say, well, maybe he could slow down by himself because that's the natural state of events, not friction, whatever. We don't know about friction, right? We never heard about it. Things, that are moving stop. From the frame of reference outside the train, for him to start slowing down means that from our frame of reference, he's starting to move. Okay, if we accept that the laws of nature are the same, then it can't be that he started to move, and by the same token, it can't be that he started to slow down. Just like to start to move, he would have needed a force acting on him. In the same way, to start slowing down, he would need a force acting. So, given this law of nature that everything is the same, independent of the frame of reference, if it's linear motion, we can deduce that to slow down needs a force, as opposed to the original conception where things just stop by themselves. Once we know that things slow down as a result of a force, we can investigate, well, what force is it? And we'll find out. There's friction, there's air resistance, and so on. Newton's first law of motion. Every body continues in its state of rest or of uniform speed in a straight line unless acted on by a non-zero net force. Okay, by now, that should make a lot of sense to you. Non-zero net force, because obviously if there's two forces acting, they cancel each other, it's not going to work out. Okay. In a state of rest or of uniform speed in a straight line. No change of direction. very, very clear to you. All right? And the property, okay, or the tendency of the body to remain in its state of motion is called inertia. It's just a word that means staying in the same state. Okay, and it's used in English in a similar sense, in other English. Oh, I just felt like inertia and I didn't get out of bed. You were in bed, you stayed in bed, so it was just like inertia, right? But that's a colloquial usage, obviously. Okay, so the first law, Newton's first law, is often called the law of inertia. Now, this law works only in what's called an inertial reference frame. Now, it sounds like a very fancy and complicated concept, but it's actually very simple. Obviously, if somebody's pushing and pulling you, or you're moving in strange ways, you might see this pen moving relative to you if you're moving like this, right? Maybe the pen is really stationary, but you're moving relative to it. If you think that you're not moving, then you'll say that the pen is moving like that. Okay, so obviously you can't say, well, see the pen, there's no forces acting on it, but it's moving. It's not moving, you're moving, and it looks like it's moving to you. All right, so you have to be in an inertial reference frame in order for this law to hold. Physics, what it is, what it's about, that it's a creative endeavor, as we showed today, hopefully not just writing an equation on the board, it's a very creative endeavor, a pen moving by itself in a straight line with a constant speed. Just imagine the pen by itself, not the whole system, not the internal, inside this pen, there are lots of forces. There's ink running back and forth, and there's molecules stretching and pulling, and atoms vibrating, and I don't know, all kinds of things happening inside, right? All kinds of things, everything in here is accelerating. All the atoms are bouncing around, the electrons are accelerating, everything's accelerating. But considered as a whole, right, we're just looking from the outside at the whole thing, there's no net forces acting on it from the outside. Okay? So if this pen were suspended or moving in space, it would be easy to see. And then you would say, really, their net forces on it are zero. Okay? Here, now my hand is part of the system. It's really my hand that's moving the pen. I'm just stuck onto it. My hand is a much more complicated system. It's hard to look at it exactly separately because it's tied in with all this stuff. All right? But if you have just an isolated body moving with constant speed, then clearly some of the forces on it are zero. Because our brain is wired according to experience, and we know that if things move around changing direction, something must be changing its direction. It can't just change direction by itself. Our experience also tells us something that is not true, that something will come to a stop by itself, even without forces. We discussed that at the beginning of the course, and we realized at the end that it's only because of friction or wind resistance and so on and so forth. But actually, without all those, it wouldn't come to a stop, and things would continue on forever without forces. Now, one of the things that's sometimes confusing is how something starts moving. All right? If the sum of the forces, if it's moving with a constant speed in the same direction, right? And it needs a force to stop or start, then if there's no forces acting on it, why is it moving at all? Was the pen always in motion? I mean, the pen was created in a factory, it wasn't always moving like this. So there must have been some force that caused it to move like this. So how do we take that? Do we take that into account? Do we have to take that into account? What is that? All right, so what happens is, let's say I picked up the pen had zero velocity. Okay? I had no acceleration and no velocity. I picked up the pen, it has all kinds of strange velocities and accelerations while I'm picking it up and moving it. And then I push it with a force, a net force, right? There's all kinds of forces and accelerations. And then I start moving it with constant speed. Now it's moving with constant speed. Now the net forces are zero. Okay, so in other words, there's a whole history beforehand that brings it to the state where it's moving with a constant speed. Force is not connected with speed. Because an object can be moving 1,000 miles an hour, there's no force on it. There was a force initially pushed it, and let it go. So we don't care about the speed when we're talking about forces. Newton's law of inertia, the first law of motion. Objects stay in their state of motion. Obviously, we're talking about if you're in an inertial reference frame, if you're not accelerating and thinking that the other thing is moving, etc. The car wheels are spinning, right? The car wheels
are spinning, there's friction, we spoke about this, there's friction between the wheels and the surface of the road. So the car pushes against, the wheels push against the tarmac or against the paved road and pull the car with them. The car pulls the back seat, and the back seat pushes against your body, and you move. All right? If you're in a car and there's a cup of coffee on the dashboard, right? And the car accelerates. Now, you are accelerating. The car is moving and is pushing you, right? If there's no friction between the bottom of the cup and the dashboard, then the car will move underneath the cup. All right? The back seat is pushing you, so you move along with the car. But as the car moves, it pulls the dashboard. As the dashboard moves, there may not be enough friction with the bottom of the cup for it to push the cup. So the cup basically stays where it was, and the car moves out from underneath it, and what will happen is then the cup will fall down to the gravity. All right? What you see, though, is you see the cup moving towards you. But it's not that the cup is moving towards you. The cup is stationary. You were being pushed along with the car towards it, towards the cup. The car moved out from under the cup, and then the cup fell. Okay? Before the cup fell, though, the cup was stationary, right? And you were moving towards it. So you see a cup moving towards you. Well, you say, well, there's no forces acting on it. Why is it moving towards me? Well, good morning, the forces are acting on you, so you can't say that if the same forces were acting on the cup, then neither you nor the cup would move with respect to each other. You would move, and the cup would move. So if the cup is in a good holder, right, then you're moving together with the cup, you're accelerating with the cup, and you don't see the cup moving. What will happen is maybe the coffee in the cup might slosh back and forth. Why? Because as the car moves, the holder moves, so the physical cup moves, and as the cup moves, it pushes against the liquid, right? But what happens when you push against one edge of a liquid? It doesn't transmit that force uniformly throughout. If you push on a book over here, all parts of the book move, right? I'm pushing here on the book, but this part of the book is moving. And it's also moving with the same speed as this part. Why? Why does this part of the book move at the same speed as this? Why is it moving at the same time and at the same speed? Is it obvious that it has to?
It's attached together, it's one piece.
Okay, it's one piece that's attached. In other words, what you're saying is that it's what we call a solid object, that the molecule over here is tightly connected to the molecule here, which is tightly connected, etc., all the way out through. So if I push on the paper molecule at the edge, it pushes on to the next molecule, which pushes to the next molecule. And this happens incredibly quickly. If it didn't happen quickly, what would I see when I push on here? When I push on this edge, right, of the book, what will happen if it wasn't transmitted? The front wouldn't move and the back would move. Another would compress, right? It would squash. And there are many things. If you push on a piece of tissue paper, that might happen, right? You push on the tissue paper, it might compress rather than the whole thing moving together. If you push on a liquid, maybe your finger will go in instead of the whole liquid moving. If you push with a wall on a liquid, it'll transmit the force, but not quite as fast as a solid.